SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to Module 2 of the Essentials of Turbulence class. Our Module 2 deals with the nature of turbulence. So in the first module, we looked at some introduction. We looked at a little bit of history of turbulence, how different physicists and mathematicians described turbulence in the early days, and what their description of turbulence was. Some tried to define turbulence, some tried to describe it in terms of certain attributes. So, since a proper definition is not out, what we are going to do in this module is look at some of the attributes in more detail. Some of the attributes that I listed out in the last module. One of them was diffusivity, another one was irregularity, the large Reynolds numbers. So we're going to look at all of that in this module. So the contents of this slide include, I'll start with the sources of course. We'll go over a little bit of introduction, just give you a refresher on some of the applications of turbulence. Then we'll look at the nature of turbulence, and that would include all the attributes in detail. Some of the methods of analysis of turbulence. We'll look at the origin of turbulence. How is it generated? Okay, what leads to turbulence? And the most important attribute of turbulence, which is the diffusivity of turbulence, we will analyze that in detail. Finally, we'll end this module by looking at length scales of turbulence. As I've already mentioned, turbulence involves a wide range of length scales. So we will focus on that particular aspect of turbulent flows, the length scales. These are the sources that I have used for this particular module. Pope's book remains. A lot of what I've used comes from observations in Tenicus and Lumley's book, as you will see, and some illustrations, figurative illustrations from some papers and conference proceedings. So as an introduction, and some of this we have already covered in the previous module, a lot of the flows that occur in nature and engineering are turbulent. I have already mentioned that. We looked at several different examples. Some more examples, some of them might be repetitive. The boundary layer in the Earth's atmosphere, that's turbulent. The jet streams in the upper troposphere, that's turbulent. And the turbulent cumulus clouds, they are turbulent. These are examples of flows that occur in nature. Another one. The water currents below the surface of the oceans are turbulent. The Gulf Stream is a turbulent wall jet kind of flow. These are again flows that occur in nature that are turbulent. Again, more examples. The photosphere of the sun, the photosphere of similar stars, they are in turbulent motion. The interstellar gas clouds, they are again turbulent. The wake of the earth, imagine the scale of that. The wake of the earth, the solar wind, is possibly a turbulent wake. What do I mean by solar wind? It's basically a continuous stream of charged particles, mostly electrons and protons, that are ejected from the outer atmosphere of the sun. Which is called the corona. So this is that continuous stream, that's a solar wind. So the turbulent wake behind the earth, where earth is acting like a bluff body, is possibly so the wake behind the earth is a turbulent flow. These are natural flows, right? Flows that occur in nature that are turbulent. An example that we have seen an illustration of in the previous module, boundary layers growing on aircraft wings are turbulent. One of the first slides in the previous module had to do with the tip vortex behind a turbulent wing. And we saw that. So these are boundary layers growing on aircraft wings. These are turbulent. These are turbulent flows. More examples in engineering. Combustion processes, and we've talked about this, that involve turbulence and often depend on it. What do I mean by that? You have the fuel and oxidizer mixing in a combustion chamber. So you have them coming and mixing together. You want the mixing to be in a turbulent manner. If it is not turbulent, that mixing is going to take time. And it might not be even efficient to make the combustion efficient. So before they burn, you want the fuel and oxidizer to mix. You want it to be a turbulent mixing so that the mixing is faster and it is more efficient. That increases the overall efficiency of the engine. So that's an engineering application. The flow of natural gas and oil in pipelines is possibly turbulent because the kind of scales that we are talking about, the size, the diameter of the pipelines, the size of the pipelines, and the rate at which you are having the flow, they are probably turbulent. Which means, what are the implications of that? What are the engineering implications of that? Stresses that are created due to the turbulent flow will determine how you design the pipeline. If it was laminar, the stresses on the pipeline would be much lesser. But because they are turbulent, the stresses on the pipe, on the surface of the pipe, are going to be very high, in which case you have to design the pipe to be strong enough. Right? So these have implications on the design of the pipeline. Another example in engineering, chemical engineers use turbulence to mix in homogeneous fluid mixtures. Let's say they are mixing two different kinds of fluids for a chemical process. They want it to mix in a turbulent manner. I talked about a simple household example in the previous module where I talked about mixing milk with coffee. You want it to be turbulent. If you mix it very slowly, if you stir it very, very slowly, in such a way that the flow is laminar, the mixing is going to be that much slower. So just like that, chemical engineers would want the mixing to be turbulent so that the process can be more efficient. More time can be saved. This could sometimes involve chemical reactions as well. So in that case, your mixing determines the rate at which they react. So if reaction is involved, in order to increase the efficiency, you want the mixing to be more efficient, you want the mixing to be faster. That's an example in engineering. Those are some examples in engineering. Another example, the flow of water in rivers and canals like we see out in nature, those are turbulent. Engineering example again, the wakes of ships, cars, submarine, aircraft, these are all turbulent motion. So numerous examples that we have seen, both in nature and in engineering, involve turbulent flows. So like I was saying earlier, the laminar flow is an exception. It is not the rule. And so we are having to deal with flows that are mostly turbulent. Mostly turbulent. In order for the flow to be laminar, we have to have either very small dimensions or very high viscosities. And it's not like that does not happen. An example would be lubricating oil in a bearing. That's mostly turbulent because we are talking clearances that are of the order of sometimes microns, or highest is probably a millimeter or so, of the order of 1 millimeter. So dimensions that are of that order, and you have fluid flows in clearances that are of the order of 1 millimeter or so, and fluids that are, for example, oil, which has a relatively high viscosity compared to, say, water or definitely air. In that case, you're talking about laminar flow. So that's an exception. That's a particular example of a laminar flow case. So that takes us to the main discussion in this module, which has to do with the nature of turbulence. And we spend a lot of time in module 1 discussing how it is difficult to describe turbulence, how it is difficult to define turbulence. And that led us to the end of module 1, where we listed out a set of attributes for turbulence. We are starting with the first such attribute, which is irregularity. And again, this is all because it is hard to define turbulence. It is hard to describe turbulence in a very definite way. Although there is a modern definition of turbulence. We saw that through different historical descriptions, right? And we have arrived now at a modern definition of turbulence, which is accepted now. That said, it is important to understand the attributes of turbulence. And one such attribute, the first such attribute that we are going to be describing is irregularity. Okay? One such characteristic of turbulent flows is their irregularity, or what we call randomness. A fully deterministic approach is very difficult, and what is our fully deterministic approach? That also we have seen in module 1. It has to do with the Navier-Stokes equations. That's the deterministic approach. A solution can be determined. So the Navier-Stokes equations forms the deterministic approach. And according to Tennekes and Lumley, and there are some contradictions here because the book was actually written in the 1970s. And we described this. This is what happens, right? The understanding of turbulence, the description of turbulence has evolved over the last few decades. So this description of Tennekes and Lumley has changed slightly, and we talk about this. A fully deterministic approach is very difficult, and so because turbulent flows are usually described statistically, according to Tennekes and Lumley. So the prevailing view at the time when Tennekes and Lumley wrote the book was that turbulent flows are random. And that is why they are arguing that the deterministic flow approach, a deterministic approach is difficult. Because if flow is random, if the flow is supposedly random, then how can a deterministic approach describe the flow, correct? So turbulent flows, according to them, are always chaotic. But again, not all chaotic flows are turbulent. So that understanding was there. But the fact that they described the flow as random, okay, that has to be noted here. Again, irregularity, okay, doesn't mean it is always random. Turbulent flows are irregular, that is for sure. The modern definition of turbulence includes that word. It is chaotic, it is seemingly random though. It is not random, it is seemingly random. It seems random to us. Because the fact that you cannot have a random behavior being described by a deterministic approach like the Navier-Stokes equations. So those two contradict each other. And like I was saying earlier, if it is random, we need something like a random kind of equations, meaning like a stochastic differential equations to describe the flow. If you're using the Navier-Stokes equations, you are accepting that they are not random. So that part is there. But nevertheless, it still remains the fact that irregularity is one of the attributes of turbulence. Turbulent flows are irregular. They are chaotic. They are seemingly random. So the only slight contradiction here from Tennekes and Lumley's description of turbulence is the fact that they are seemingly random as opposed to they are random as described in their book. The next and probably the most important attribute of turbulence is the diffusivity. So diffusivity is a very important attribute of turbulence. So I show this by through this figurative illustration where I have these jets of water that are emanating. And we have talked about this briefly at least. The diffusivity is the enhanced mixing of turbulence, the enhanced mixing feature of turbulence. It causes rapid mixing and increased rates of momentum transfer, heat transfer, mass transfer. A flow that looks random but does not exhibit the spreading of velocity fluctuations through the surrounding fluids is not turbulent. So what do I mean by that? It might seem random to us, so irregular in other words, but if it does not have the feature of spreading these velocity fluctuations, in other words, single word, diffusivity. If it does not have diffusivity, it is not turbulent. That is one of the main requirements of it being turbulent. So a flow might look chaotic, might look irregular, but if it does not have diffusivity, it is not turbulent. If it is not diffusive, it is not turbulent. And here again, one example that I want to bring here is the contrails of an aircraft. So if you don't know what the contrails of an aircraft is, sometimes if you look in the sky where you have a passenger jet that is traveling through the air at a very high altitude, and you see it almost like a speck that is traveling, but you see a trail of smoke-like thing that is behind the aircraft, and that trail, also called contrails, extend for a very long distance, sometimes even miles. Now, why does that happen? The water vapor from the exhaust of the exhaust of the aircraft is condensing, and that is causing that white smoke-like behavior. The fact that it is extending for miles means maybe near the jet, near the exhaust, they are turbulent. So they are probably generated turbulent. However, they are not turbulent as over the miles that you see them. They might look turbulent to us. So again, if you look at them, you will see that there is some irregularity in the way the trails are. However, they are not turbulent. If they were turbulent, they would have not extended miles. They would have not extended in miles like you see in the sky. So that is that diffusivity. If there was enhanced diffusion, they would have mixed with the atmosphere. The fact that they are extending for miles means they are not turbulent. They are irregular, but they are not turbulent. Another example, let's say smoke from the chimney of a factory, of an industrial factory that is coming out. Let's say you have the black smoke coming out. So here it is turbulent. The atmosphere, the boundary layer, there is probably some wind that is creating some kind of turbulent flow at that altitude. So what happens is you will see that probably within a few meters the smoke sort of diffuses into the atmosphere. If the flow was not turbulent, in other words, if the flow was laminar, you will see that black smoke extending for several hundreds of meters. Hundreds of meters is just an example. But within a few meters, it sort of mixes with the air, and you don't see that smoke anymore because it has diffused with the atmosphere. That is diffusivity. Two examples, right? Contrails of an aircraft where it is actually not turbulent, and smoke from a chimney where in most of the cases it is actually turbulent. So that diffusivity is something to keep in mind. So this is what I'm saying. If a flow pattern looks random but does not exhibit the spreading of fluctuations, then it is surely not turbulent. Okay, some examples where it's the single most feature as far as turbulent flows are concerned, right? It prevents boundary layer separation on airfoil at large angles of attack, although it's not like you can have the angles of attack really large, not too large, okay? But still, it prevents boundary layer separation at relatively large angles of attack. It increases heat transfer rate in machinery. It is the source of resistance for flow in pipelines, and it increases momentum transfer between wind and ocean currents. So the smoke coming from a chimney, that again is an example where the momentum is transferred. And because the flow is turbulent, the momentum transfer is much faster. So that enhanced diffusion, that diffusivity is the single most important feature. Moving on to the third attribute, which is large Reynolds numbers. So I want to illustrate this figure. This one shows here a jet, a turbulent jet emanating out of a nozzle. So again, we knew this. Turbulent flows always occur at high Reynolds numbers. You have a complex interaction between viscous and inertia terms, and that is exhibited through a single parameter, right? The Reynolds number that came out of Reynolds experiments. So you have this jet that is emanating, and around the jet you have sort of a quiescent environment. So essentially laminar, low Reynolds numbers free stream flow. And the jet itself is at high speed or large Reynolds numbers, and that you have a turbulent high Reynolds number jet. So complex interaction between viscous terms and inertia terms. So I want to talk about that, and if I look at the Navier-Stokes equations, I have ut plus u dot del u is a vector here, equals minus 1 over rho del p plus nu del squared u. Isn't it? Nu is the kinematic viscosity. So we are talking about nonlinear term, inertia or convective, and viscous. So the turbulent flow, the Reynolds numbers, is basically a competition between these two terms, inertia and viscous. You have the unsteady term on the left, the first term on the left hand side, inertia term, pressure gradient, and then viscous term. And this large Reynolds number or low Reynolds number basically is a balance between viscous and inertia. And that is clear when you think about Re being inertia over viscous. That's what we mean by that. So this interaction is very complex, right? I mean, we can always say that as inertia terms increases, Reynolds number increases. As inertia term reduces, Reynolds number decreases. Okay, so this occurs, and this is leading to the method of analysis and the origin of turbulence as well. It originates as the instability of laminar flows starts propagating if the Reynolds number is large. If the Reynolds number is low, there is no mechanism for that instability to propagate further. It will get dissipated because of the high viscous nature of the flow. I'm talking about laminar flow. In a turbulent flow, on the other hand, when the inertia terms are high and the viscous terms are relatively low, the mechanism, the inertia, what it does is it tends to propagate the instability. That instability keeps growing and leads to turbulent flow. So the nonlinear part, as I had mentioned before, the nonlinear part is what makes these set of equations bit more complex, right? Because coming up with a solution for this is next to impossible, an analytical solution. And obviously the randomness, and again this comes from Tennekes and Lumley's observation, but we now know that it is a seemingly random behavior rather than just the randomness. So in order to solve these equations, a lot of concepts and tools have been developed, but we now know that you cannot rely on equations alone in order to come up with the solution to this problem. And that large Reynolds number is what makes it extremely complex. The large Reynolds number coming because the inertia term is much higher, much more dominant compared to the viscous term. So the nonlinear term has an effect, and that nonlinearity makes these equations intractable to solve. The next attribute are three-dimensional vorticity fluctuations. So again, if I think about vorticity, it is the curl of velocity, right? Omega, which is a vorticity, is a vector again, and it is described as del cross u, where u is the velocity vector. So it is the curl of the velocity vector. That's the definition. So you can actually get three different terms for omega: omega I, omega j, and omega k. So we know that turbulent flows are rotational, okay, as in vorticity is non-zero. And this is something that I had mentioned earlier as well. The stretching of three-dimensional vortices, we now know that it plays a key role in turbulence. What do I mean by that? I'll consider the vorticity transport equation, and we'll talk about this in detail as well, more detail as well. I have d omega dt. So notice that I'm using capital D, which is the total derivative or the substantial derivative, is omega dot del u. Omega is a vector, plus nu del squared omega. Okay, so the left hand side is obviously del omega del t plus u dot del omega equals omega dot del u plus nu del squared omega. This term here is the vortex stretching term. We now know that the vortex stretching is primarily responsible for the breakup of vortices. So it has a big role to play in vorticity dynamics. And the fact that omega is a curl of velocity. Omega is a curl of velocity. So if the flow was two-dimensional, the omega would only have one component, the z component. So if flow is two-dimensional, as in if you for 2D, the velocity vector is ux and uy. If in two-dimensional flow, velocity vector is ux and uy, then omega is purely just omega z, in which case the vortex stretching term goes to 0. So omega dot del u is equal to 0 in 2D. In 3D, on the other hand, u is ux, uy and uz, and omega is omega x, omega y and omega z, in which case omega dot del u is not equal to 0. So you can derive this on your own. We will in fact go through the derivations in the next few modules or so. But the vortex stretching term is 0 in 2D flows, which means if the vortex stretching term is 0 in two-dimensional flows, what is actually creating the turbulence? What is creating the breakup of the vortices in 2D flows? So that's what we mean by turbulent flows are 3D. They are three-dimensional and they have vorticity. They have a non-zero vorticity. That's what we mean by that. So the vorticity dynamics plays an essential role, right? And the second point is what I was just mentioning. The vortex stretching term is absent in 2D flows. So an example would be, flows that are substantially 2D, such as cyclones in the atmosphere, which determine the weather. They are not turbulent themselves. They are 2D, but they look turbulent, but they are not turbulent because they will not have the vortex stretching term. Another example, random waves on the surface of the oceans. They are not turbulent motion, as they are essentially irrotational. They are irrotational. They don't have vorticity. So those are some of the attributes that we have discussed here. Like I said, we started describing the attributes mainly because we are not able to come up with a proper definition. There is a modern definition that is accepted now. However, it is important to describe turbulence in terms of the attributes. And the attributes were, we started with irregularity, correct? We started with irregularity. We talked about how turbulent flows are irregular, seemingly random, according to the modern definition, although Tenicus and Lumley described it as random. Diffusivity, single most important feature, attribute of turbulence, diffusivity. And the large Reynolds numbers, the interaction between inertia and viscous, that leads to the Reynolds numbers. And then finally, the 3D vorticity fluctuations. So those were the 4 attributes that we have discussed in this particular class. We'll discuss more attributes in the next class. Thank you.